Imagine saying goodbye to your twin brother. You're both 25 years old. You board a spacecraft capable of traveling near the speed of light. Your brother stays on Earth. For you, the journey lasts only 5 years, but when you finally return home, your brother is 75 years old. You are still 30. He's an old man. How is that possible? Did you travel into the future? Did time itself slow down? Or does the universe somehow treat two identical people differently? This is the twin paradox, one of the strangest consequences of Einstein's theory of relativity. And unlike many science fiction concepts, this one is real. Scientists have tested it. Satellites experience it. Astronauts experience it. Even your GPS system depends on it. Today we're going to explore one of the most mind-bending ideas in modern physics. Because according to the universe, time is not what you think it is. Imagine identical twins. Let's call them Alex and James. Both are born on the same day. They grow up together. They celebrate every birthday together. Their clocks always agree. At age 25, Alex volunteers for an incredible mission. A spacecraft has been built that can travel at 99.5% of the speed of light. Alex climbs aboard. James remains on Earth. The mission is simple: travel to a distant star and return. From Alex's perspective, the journey feels surprisingly short. He eats meals, sleeps, reads books, looks out the window. His clock keeps ticking normally. His heartbeat feels normal. Everything seems perfectly ordinary. 5 years pass. Alex returns to Earth, but something impossible has happened. James is no longer 30 years old. He is now an old man. Decades have passed on Earth. The twins are no longer the same age. One traveled into the future, but which one? Before Albert Einstein, scientists believed time was universal. Everyone shared the same clock. 1 second was 1 second for everyone, no matter where you were, no matter how fast you moved. Then, in 1905, Einstein introduced the theory of special relativity, and everything changed. He proposed two revolutionary ideas. First, the laws of physics are the same everywhere. Second, the speed of light is constant. No matter how fast you move, light always travels at the same speed. This creates a problem. If light's speed cannot change, then something else must, and that something is time itself. Time slows down for objects moving at extremely high speeds. This effect is called time dilation. The faster you move, the slower your clock runs compared to someone standing still. At everyday speeds, the effect is tiny. Driving a car won't make you younger. Flying on an airplane changes time by only billionths of a second. But as you approach the speed of light, the effect becomes enormous. And this is where the twin paradox begins.
At first, the paradox seems confusing. From Earth, James sees Alex moving. Therefore, Alex's clock should run slower. But from Alex's point of view, Earth appears to be moving. Shouldn't James age more slowly instead? Who is correct? The answer lies in something very important. The two twins are not experiencing the same journey. James remains in one frame of reference. Alex accelerates. He turns around, he changes direction. He experiences forces. Alex's journey is not symmetrical. This breaks the apparent contradiction. The traveling twin changes reference frames. The earthbound twin does not. And because of that difference, less time passes for Alex. The universe keeps perfect accounting. There is no contradiction, only a reality that feels deeply counterintuitive.
Many people think relativity is merely a mathematical trick, but time dilation is real. Scientists have measured it repeatedly. Atomic clocks placed aboard airplanes have returned slightly behind clocks on Earth. Fast-moving particles created in Earth's atmosphere survive longer because their internal clocks slow down. Even astronauts aboard the International Space Station experience tiny amounts of time travel. After months in orbit, they return to Earth, having aged slightly less than people on the ground. The difference is small, only milliseconds. But the effect is real. GPS satellites must constantly correct for relativistic time differences. Without these corrections, navigation errors would grow by kilometers every day. Your smartphone works because Einstein was right. Time truly changes. Suppose humans build a spacecraft capable of traveling at 99.99% the speed of light. A star lies 50 light-years away. For people on Earth, the trip requires decades, but for the astronauts on board,
Time slows dramatically. The journey may feel like only a few years. When they return, centuries could have passed on Earth. Everyone they knew would be gone. Cities would have changed. Languages might evolve. Civilizations could rise and fall. The astronauts would become visitors from the past. They would have traveled into Earth's future without breaking the speed of light, without entering a wormhole, without a time machine, simply by moving very fast. This is perhaps the most astonishing prediction of relativity. The future is accessible, the past is not. The twin paradox teaches us something profound. There's no universal clock, no cosmic stopwatch ticking for everyone. Every observer carries their own personal time. Your experience of time depends on your motion through space. The faster you move through space, the slower you move through time. Space and time are not separate. They are woven together into a single fabric called space-time. Einstein showed that movement through one affects movement through the other. This idea completely changed our understanding of reality. Time is not absolute. It is flexible, stretchable, relative, and deeply connected to the universe itself. Could future civilizations use time dilation intentionally? Perhaps. A person diagnosed with an incurable disease might travel near light speed. For them, only a few years would pass. But centuries could pass on Earth. They could arrive in a future where medicine has advanced. Interstellar explorers might travel to distant galaxies while experiencing only decades. Generations on Earth would come and go, but the travelers would remain relatively young.
This may become humanity's first practical form of time travel, not backward, only forward. Einstein's equations allow it. Nature permits it. The challenge is technology. Reaching near light speeds requires enormous amounts of energy.
Today, such journeys remain far beyond our capabilities, but the physics says it can happen. Beyond the equations lies something deeply human. Imagine returning home. Everyone you love has grown old. Your parents are gone, your friends are gone, entire generations have lived and died. The world has moved forward without you. You remain young. The universe has given you extra time, but it has taken something away in return. The twin paradox is not merely about physics. It is about separation, about time, about what it means to grow old, and about the price of exploring the stars. Perhaps future astronauts will face this reality. Perhaps one day someone will leave Earth and return to a civilization they no longer recognize. The mathematics predicts it. The universe allows it, and that possibility makes the stars feel both exciting and heartbreaking. The twin paradox reveals a truth that seems impossible. Two people can begin life together, live through different journeys, and experience different amounts of time, not because their clocks are broken, but because time itself is different for each of them. The faster you travel, the slower time flows, and somewhere in the distant future, humanity may use this strange property of the universe to reach the stars. Because, according to Einstein, time is not fixed. It bends, it stretches, it changes. And perhaps the greatest paradox of all is this: the more we learn about time, the stranger it becomes. If you enjoyed this journey through the universe, remember to subscribe, because the cosmos still holds many mysteries waiting to be explored. And until next time, keep looking up.